By far, the largest and most common challenge I've seen people new to creating procedural shaders have is figuring out how to translate their intentions into math. And today I want to make at least a part of that a lot easier for you. Let me explain what I mean by that. Fundamentally, every part of how a computer works eventually boils down to math at some level, but as a user you don't need to interact with that math. You click a button and Chrome opens. You don't need to think about all the math that goes into just determining that you clicked a button, let alone everything that goes into running the internet. Because your computer has a user interface, you can go directly from intention, I want to watch YouTube, to action. You click the Chrome icon and it opens. Every time you create a material in Blender, you're actually creating a new program that tells your graphics card how to render a surface. And in creating that program, you are programming and must now interact with your computer on a lower level. This comes with a lot of freedom, as you can now tell your computer exactly what you want it to do, but to do so you need to speak its language, or at least a language you both understand. There is now another step in the process. You can't go directly from intention to action, but first need to translate your intention into instructions that the computer can understand and act upon. With shaders, I'm simplifying it a bit here, but this mostly means translating it directly into math, which is not an intuitive thing to do. However, programmers have been struggling with translating intention into instruction for a long time, and there are a lot of lessons that we can pull from the programming world to make creating procedural shaders much more manageable and intuitive. In particular, I'm going to talk about how you can use abstraction to make your shaders more declarative. That just means that instead of needing to think about all the steps that a computer needs to go through to do a thing every time you want it to do that thing, you can abstract all those instructions into a single instruction that represents your intention for what that group of instructions accomplishes. If that doesn't quite make sense yet, just keep watching. I promise it'll make sense by the end. And to help you understand this, I'm also going to teach you how to create logic gates that you can use in your shaders. This is because they're a great example to illustrate this concept. They're incredibly simple to build, and they also show that this isn't a strategy that needs to be reserved for very large node graphs, but can, and I think should, be used for very small ones as well. So what are logic gates? Logic gates are a way to compare or ask questions about two or more existing conditions. If I have condition A and condition B, which are each either true or false, I can use a logic gate to give me a single value at the end, depending on which question I'm asking. There are 7 different logic gates, but they're built on top of 3 fundamental questions. Are any of the conditions true? Are all of the conditions true? Or are the outputs of the conditions different from each other? Logic gates operate on binary data, true or false, sometimes represented as 0 or 1. This is why I think they're best suited for working with masks, as a mask is just a texture full of binary data. Sometimes masks do have shades of gray, and we'll need to decide how to handle that later, but to keep it simple for now, we'll just think of masks as exclusively black or white. Masks are very useful because they work on the principle that anything multiplied by 1 stays the same and anything multiplied by 0 becomes 0. This means that we can use a mask to isolate effects or operations to specific areas. The simplest example of this is just plugging a grayscale texture into a factor slider. Where logic gates come in handy is when you need to combine multiple masks into a new mask. Think, what parts of the model are affected by ambient occlusion and are facing downwards? Or, where is this height map greater than 0.5 or the model should be affected by Fresnel? Or even, tell me when these two objects are within this distance to each other or are near the world origin, but not both. These are fairly simple questions, and the math is pretty simple as well, but it's not intuitive, which is what trips people up. This is where logic gates come in. If you have your conditions already, you can just use the logic gates to ask these questions directly rather than needing to remember what the math behind them is, which makes everything a lot more intuitive. Before we get into how to build the logic gates, I want to quickly mention that if you don't want to build the logic gates yourself, I have prepared a file for purchase. It's only $1 and you get a more polished and asset browser compatible version of what I show here. If that's something you're interested in, I'll leave a link in the description. The easiest way to show you what each of the logic gates do is with something called a truth table, which is a table that allows us to see all of the possible combinations and their outputs to make sure that everything is working properly. I've made one here just by separating out the UV coordinates and using greater than 0.5 nodes on both the X and Y coordinates, which gives us 2 masks we can use logic gates on to see how they handle all possible combinations, which is when no condition is true, where only one condition is true, and where both conditions are true. The simplest logic gate is the NOT gate, which is only sort of a logic gate because it only operates on a single mask rather than 2, but it's useful nonetheless, and it's used to help make 3 of the other 6 gates. The NOT gate simply inverts its input. What's true becomes false, and what's false becomes true, and the math behind this is simply 1 minus your input. Where your input is false, it inputs 0, and 1 minus 0 is still 1, which is true. Where your input is true, it inputs 1, and 1 minus 1 is 0, which is false. However, this does assume that your input is always 1 or 0, and because our input is a float value, this isn't necessarily true, and it can potentially be any number, and if we don't handle what happens if the input is something other than 1 or 0, it could lead to all sorts of unexpected behavior. The math works out that we can just click the clamp check on the subtraction node and we'll get the same output as if we had clamped our input. This handles input outside the 0 to 1 range, but now we need to decide what we want to do with values between 0 and 1. The most traditional solution would be to round up or seal it, as traditionally, when programming, 0 is treated as false and anything other than 0 is true. You could also round down or floor the value, so that it needs to actually hit 1 to be treated as true, or just round to the nearest value if you want. However, for shaders I want to make the case that we should instead do nothing and leave the values as they are, because gray values are very useful in masks as a way to partially apply effects and, in my opinion, should be preserved. So now that we figured out how to make our finished NOT gate, which is really just a subtract node set up in a specific way, we can abstract this out into a node group that represents our intention, which is to act like a NOT gate or to invert its input. To finish setting up our group, I'll rename it to NOT gate and remove the extra input it added, then set it off to the side for now. Onto the first of the 2 input logic gates, the OR gate. This gate should output true if any of its inputs are true. Looking at our truth table, if we have it set up correctly, we should see a sort of reversed L in white and then a small square in the corner where it's black. For this, we'll use a clamped maximum node. The maximum node just outputs whichever of its inputs has the largest value. So if we look at the bottom left square, it's false in one mask and true in the other, so the node outputs true for that square because it has at least one true input. Again, now that we figured out the math, we can abstract it out into intention by turning this into a group, and I'll rename it to OR and then set it off to the side with our NOT gate. The next node you can kind of think of as the mirror or shadow of the OR gate, and that's the Xnor Gate or not OR gate, which, as the name implies, is just an OR gate followed by a NOT gate. If we look at the output, the only true square is the one that is false in both of our inputs. So, while the OR gate tells us where any input is true, the Xnor Gate tells us where no input is true. Again, we'll abstract this into a single node by grouping them together and renaming it to Xnor. The next node is the AND gate. This node should only output true when both of the inputs are true. This is the node you would use to ask what areas are true in mask A and in mask B. Looking at our truth table, if we set up the gate correctly, we would expect to see only white in this bottom corner where the true part of both inputs overlap. To achieve this, we'll use a clamped minimum node. Then we can abstract away the math again by turning it into a group and naming it AND. I'm sure that you can guess that since there's a not OR gate, that there's also a not AND gate, and you build it very similar to the NOR gate by combining an AND gate with a NOT gate. The NAND gate is sort of like the inverse of the OR gate, where the OR gate returns true if any inputs are true, the NAND gate returns true if any of the inputs are false, which is useful for finding where masks don't overlap. Onto the last pair of gates, we have the XOR gate, or exclusive OR gate, depending on how you want to say it. The XOR gate returns true if the inputs are different and false if they're the same. So looking at our truth table, we would expect to see a sort of checker pattern, where it's black in the corners where both inputs are either false or true, and then white in the other corners where only one input is true. Technically speaking, I think this definition is incorrect. I believe the actual definition is that a XOR gate should return true if the number of true inputs is odd. However, practically speaking, when people use it, they use it to determine if the inputs are different, and this is what I'm going to show you how to build. Now, the most intuitive way to find how different the values are is to take the larger value and subtract the smaller value. And you can do this by taking the maximum of the two values and the minimum of the values, and then subtracting the minimum from the maximum. And if you clamp the minimum and maximum nodes, this works perfectly fine. However, there's a way to do this that should be a little bit more efficient. We first clamp both of our inputs because we only care about the 0 to 1 range. Then, plug both of our inputs into a subtraction node. The order you plug them in won't matter in the end, but right now we are getting different results depending on the order that you plug them in. This is because we're getting the difference from the first socket to the second, but we don't want the difference, we want the distance. So we'll put this through an absolute value node, which changes everything to be positive, and this is now the distance between the two inputs. And the distance stays the same regardless of the order that our inputs are plugged in. This gives us the same result that we had earlier, but this should be a bit faster as there's no branching or comparisons that need to be done. Your computer can just run straight through the math. Now that we figured out the math, let's abstract it away into a group, and then I'll rename it to Xor. And now onto the final logic gate, the Xnor Gate, or exclusive not or gate, depending on how you want to say it. And I'm sure you can guess that this node is just the inverted Xor Gate, where the Xor Gate tells us where masks are different, the Xnor Gate tells us where they're the same. For one final time this episode, we'll turn this into a group and rename it to Xnor. Now we have our final set of logic gates. I hope that was helpful in illustrating how you can use node groups to create abstractions of your logic that can then be used to represent your intentions. Now that can make it easier to translate from your intention to instructions for the computer. Just a reminder that there are links in the description if you want to purchase a version of these nodes that are a bit more polished and asset browser compatible. They're functionally the same as what I showed here, they're just a bit nicer to use and it only costs $1. If you've enjoyed this video, you can tell both me and YouTube that by liking and subscribing. If you have any questions, I'd be happy to answer them in the comments, or you can join the new channel Discord, linked in the description. Thanks for sticking around to the end, I'll see you next time.